Hello there. Welcome to another problem session. So today we have a really practical problem, right? So this is a device that's called Helmholtz coil. So basically, there are two coils, but it's just called Helmholtz one coil, just not plural. In this structure, you have a coil here of several turns and same number of turns over here. So you can have a current come in and kind of say go over here. There's some schematic drawing of it comes in, and you can see it then goes into the other coil. If the current is running in the same direction, you call Helmholtz coil, and the current is running in the opposite direction in one. I mean, you might say, okay, how do I do an opposite direction? So instead of this going here, this will go here and this will go here, then the current will go in the opposite direction. So the current is going in the opposite direction, then it's called anti-Helmholtz coil. But I'm going to do Helmholtz coil here. And over here is even more schematic drawing. So all these coils are just given like one circular thing with total current N times I, N being the number of turns, and N is a number of terms here, and there are N terms here. So each one, just replace each one of them is just one single loop, and it's just loop. And the radius of that loop is capital R, and the distance between them is also capital R. And we are interested in a very small region around the center. We're going to answer all the questions near the origin. The first one is about getting how it varies along the z-axis. Okay. And the second question is, what's the if the magnetic field is in, if it was just a circle like that, and at the origin, it will. Both of them will point it up. So this was just a z component. The bz will be the net b. It will be same here. Now, if I have a this is the reason. Number 3 is the reason why this coil is used. Is because around here, the magnetic field is really uniform, very uniform. So once you set it up, if you're looking for an extremely stable and uniform field, you'll use Helmholtz coil. It's not that difficult to make, so it's really used a lot because of this reason. Because the B is at O or near O, will be very uniform, and you can show by showing that the derivatives of the B with respect to like dB, dz, and looking at just the z component, these like if I z equal to 0, it will be 0, second derivative is 0, and third derivative will be 0, and you're supposed to find the lowest derivative that's not 0. So the way number 3 will be done is you will use 1, you will have a b, let's say b, just b of z as a function of z along this axis, and then x equal to 0, y equal to 0 assumed, okay? And then you're gonna expand in, so you're gonna write b of z in terms of epsilon equal to z over r, and then you're going to expand bz 0 plus dbz d epsilon, which is going to replace z by z over r, that variable. Epsilon equal to 0, epsilon plus d square bz d epsilon square, epsilon equal to 0. You're going to do some expansion like that and see which one is the first non-zero term. That's what we're supposed to find. Okay. So now that I've explained the problem, maybe you can take your time and try to do this out on your own. A problem that will be helpful to you is the answer to this. Suppose I have just one loop, this circular loop, radius r, and on the z-axis, some point, let's call it arbitrary z. What's the magnetic field from a current I? So what's the formula for this? First you work that formula and see you can use that formula to write a contribution from here and a contribution from here. Be careful when you're trying to use the formula, this formula, because this one, you know, this formula has the origin here, and here the origin is here. So it's a little bit translation problem, but from here to here, you can probably solve all of these. Okay, with that hint, I'm going to pause and see if you can attempt on your own, and then you can come back and we'll do it. Okay, so here is like a brief Biot-Savart formula for it, right? Derivation. So this is you can do B, it will be this formula, and when you work it out, the dB for that corresponding to that will be in that direction, 90 degrees to that. And then you can just say projection of this along that direction is needed. So that's the theta. So this R over big R. So one of these R and 1/3 power of that is this script R. And so this is the formula that I have derived before in some other video, and you can also go there to see the derivation. Okay. That reminds me, if you haven't subscribed, really I would like to ask you to subscribe. It helps this channel grow. And if you like this kind of explanation, definitely hit a like button. Maybe you can hit it now, so you can actually help grow the channel. And also tell your friends and tell your friends and teacher maybe so about this channel and this website. So appreciate that. Thank you. Okay, now let's get back to it. Now this is, you can see between here and here is very similar, except that this coordinate system is not the same as this coordinate system. So let's call this guy if you're going to call this Z with the origin here, I can call this as a Z prime with origin O prime. Okay, so, and this coordinate Z prime, and this will be like Z prime and Z prime, Z prime, and this is just a component description, like the, you know, the Z component. This is not a function, this is the function variable, right? This is the one locates where this is. Okay, so if I have this Z axis with origin here and Z prime axis with origin over here, say I'm working with this one, then I'll work with that a little bit later. Then you can, and this is R over 2, this distance R over 2, then you can see the Z is Z prime minus R over 2, because when Z prime is R over 2, then Z is 0. So from this, all I have to do is Z prime equals to Z plus R over 2. That's all I have to replace. So let's call it C1 and C2, that's the circuits. So B1 from this circuit at Z will be just mu naught ni r square over 2, 1 over r square plus z plus r over 2 square, and this whole thing 3/2. So how about that guy? Well, let's call that z same way. Okay, so we have the original z with O, then this z prime, you can put it up there or there, it doesn't matter, this z prime, and this distance is r over 2, so you can call it z double prime, and that will be O. Z double prime will be okay, so when this is the field point, you know, and that's where the loop is. So from here to here, now you have a actually exactly opposite, z equal to z double prime plus r over 2. When z double prime is 0, z is r over 2, right? So this is so for b2 z will be just z minus r over 2. Z double prime is z minus r over 2. So this loop thing would just look like very similar. Ni r square over 2, 1 over r square plus z minus r over 2 square, 3/2. So I add this b of z, this net will be just these two together, b1 z plus b2 z, because they're in the same direction. If you can look at right hand rule, use the right hand rule. So b2 is that direction, and if you do it like that, if you do it like that for the lower loop, and b1 will be in the same direction. b1 and b2 will be in the same direction. Okay, so we have our answer, and so we have an answer for 1. For 0, at the origin, we'll just set the z equal to 0, right? So for number 2, this we already answered number 1, and for number 2 we set z equal to 0, so right to the center between the two loops. So if we set z equal to 0, then it's going to be these this and this become the same. So b at z equal to 0 is going to be 2 times mu naught ni r square over 2 times 1 over r square plus you have a r square over 4, 3/2. So let's simplify it. So this is going to be 5. So this whole thing is a 5/4 r square, and this cancels out. So this is 4/5. It's going to flip, and that's going to be 3/2 mu naught ni, and you'll have an r cube, and that over r. That should be this should be it. Yeah, I think that's the answer for 2. And the 3 is going to be a little bit longer answer, so let me erase and try to work that out. Okay, so rather than really expand it in a very complicated way, taking a Taylor series directly, if I can convert this into some kind of a binomial expression, like 1 plus some kind of a, which is a is less than 1 for us, okay? Doesn't have to be, but say if I convert that to this, but the p can be fraction, numerical value. So we'll see p equals to minus 3/2 for us. So this will be 1 plus p times a plus p times p minus 1/2 factorial times a square plus p times p minus 1 times p minus 2/3 factorial a cube plus p times p minus 1 p minus 2 p minus 3/4 factorial e to the 4, etc. So if we can convert this into that, we convert into something like that, it will be really nice. So clearly one thing we can do is pull r out completely. So it's going to be r cube, and this will become 1, and this will become 1, and this will become z/r, and this will become 1, and this will z/r, and this will become 1. So I put all the r out, and z/r is small, so we want z/r much less than 1, like z is much less than r. That's what we want. So we can call this guy, we can call this epsilon, and call this epsilon. So epsilon equal to z/r. Now let's see, if I expand this, then I get 1 plus epsilon square plus epsilon plus 1/4. When I expand this guy, I get 1 plus epsilon square minus epsilon plus 1/4. So this is still big. I still not like that. So this with that will become 5/4 plus epsilon square plus epsilon, and this is 5/4 plus epsilon square minus epsilon. And so if I pull 5/4 out from all of this, then I can write this as a 5/4, 1 plus 4/5 epsilon square plus epsilon, and 5/4, 1 plus 4/5 epsilon square minus epsilon. See, now I can call this guy a b, and call this guy a. Then if I'm done with pulling all the things out, let's cancel this guy, mu naught ni/2r. Then I pull this guy 3/2 power, so this is going to be 4/5 to the power 3/2. So I have, from the first expression, I have 1 plus a to the power 3/2, and from that second expression I have 1 plus b to the power 3/2, and a equals to 4/5 epsilon square plus epsilon, and b equals to 4/5 epsilon square minus epsilon. So after I expand this, we should have a very easy expression to work with. Let's see if we can. All right, I hope this is clear to you now. So what do I get now from each one of them? So let's just look at this part, okay? That part no need to carry. So we have, the first one is, so this is equal to -3, and this is equal to -3. So P equals to -3/2. Okay, and if I do A, I get 1 minus 3/2 A and then I get a plus half, that's minus 3 half minus 5 half a square. Then I get a plus half minus 3 half minus 5 half, this 1/6, this one, minus 7 half a cube. And then we have 1/4 factorial, which is 24, minus 3 half minus 5 half minus 7 half minus 9 half e to the 4, etc. And then I've got the same thing, 1 minus 3 half. So this whole thing, same thing, A goes to B. Okay. No need to just repeat that, right? So let's see how much that, in terms of same power epsilon, that coming from here and here. We're not interested in A or B, we're interested in epsilon. We need to have same power epsilon. So if I look at this as 1 minus 3/2, A is this stuff, 4/5 epsilon plus epsilon square, and then I have a half, and that's minus plus 15/8. A square is A square will be 16/25. Epsilon plus epsilon square is square. Then we'll have a this minus this plus, then it's going to be minus, and then this quantity over here, and then we're going to add. You can see the B is everything where you see epsilon goes to minus epsilon. So right away you can tell all the odd powers of epsilon will be 0, right? So like epsilon to the power 0, we'll get 1 here and 1 here. 1 plus 1. So that will be 2. Epsilon to the power 1, whatever you're going to get, and then you're going to get exactly same but negative from the B. This is coming from B, and this whole thing is coming from A, using A and using B. So this will cancel out, that will be 0. Epsilon to the power 2, I'm going to get minus, from this I'm going to get minus from this guy, and so 12/10 from this, or maybe 6/5, 6/5 from this, and then from here square it, and then we're going to get a plus, so 15 times, so you have a 15 times 2/25, and so this from the A part. Let's see, then this, and so this guy cancels, plus the B part. So A part is 0, and exactly same terms come into the B part, and that's also 0. So this is 0. Epsilon cube term, of course I got whatever plus negative of the same, so this goes 0. Epsilon to the power 4 is going to be nothing from here, nothing from here. This is the first term I'm going to get. It's going to go, so when I square it, factor is 1, and then this whole thing, there's this is over here, like 6 over 5. So plus 6 over 5. And over here, you can see you're going to get when you expand this, you get a epsilon cube, and then this square times this, 3 epsilon square, and then epsilon to the 4. I mean, then this square, this cube times 1 power of that, right? This cube and 0 power, this square and 1 power, this and that square, so the epsilon to the power 5 and then epsilon to the power 6. So we want this, so it's going to be minus 3 times this stuff over here, 35, and over there is times 4 over 125, 7, 25. So from there, and then 4th power will come from here, and then that will be this whole humongous thing, 315, 60, okay, that times 2, this becomes 1, 125 over 5. And this whole thing is coming from the A alone, and the B will be exactly the same thing, so times 2. And this is not 0. So when I expand this, I am going to get epsilon to the power 4 at the first term non-cancelling. Okay, so working out, we got 2 here, and we got 2 of these guys. So let's call this some quantity C, 2C. So you got a 2C, but 2C is multiplying epsilon to the power 4, and that's epsilon is equal to Z over R to the power 4. So that's the first non-rising terms. I could continue. So this is the answer. So this is if I do dBz, dz z equal to this 0, and the second derivative is 0, d is 0, third derivative is 0, and only first derivative is going to be over here. You can see fourth derivative will be d4, derivative will be this whole thing. So for the fourth derivative will be d4th bz dz to the power 4 z equal to 0 is going to be this stuff times 2 times 4 times 3 times 2 times 1. Because I take 4 derivatives, everything, all of this z to the 4 power go away, and that is the answer for the fourth derivative. So it's very uniform. You know, it's like this is the constant term, and this thing very little change. As long as you're close to the center, it's not changing that much. Okay. What are the kind of typical things that people use in the lab? You know, the R can be like 5 centimeters, something like that. The current can be 2 amp. N can be like 250 turns or some. So you may want to work it out with these values. What will be the magnetic field? How strong is B? You may want to work out. As a reference, magnetic field of the Earth is about 10 to the power 4 Tesla. actually half times 10 to the 4 Tesla. 10 to the 4 Tesla is called a Gauss. Okay, I think this is a lot of algebra, and I'm sorry that this is kind of like a messed up my work a lot. And when I was doing this algebra, I did make some copying errors, and I had to redo this video. So some of the things you might want to remember is this is a really nice trick to remember, that whenever you come to an expansion, normally it's, if you can put it as a binomial expansion, after that you're cool. Things will go pretty smoothly after that. Okay, another thing that remember is how to do it for one loop. That's one of the things you should know how to do. And the third thing is, when we change, you don't have to redo the problem. You just have to redo the coordinate change, so they can get it for the loop being at a different place along the axis. And that actually gets tested a lot. You know, they give you this answer for one, and then they can ask you, well, I've got one loop here, one loop here, one loop here. What's the magnetic field over there? So this is common question people like to ask, because from here, 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 you should be able to tell what's on the axis if you know the answer for that. Okay, take care. Bye.